Many prophets of doom and gloom constantly predict the most horrendous woes that would befall us. Think of Y2K. On the 1st of January of the year 2000, many computers were supposedly going to stop working, and that would be the end of society as we knew it. Didn't happen. Life went on. Yes, a couple of computers were really affected, but they were generally fixed well ahead of schedule and didn't cause any real problems on the 1st of January. In the case of networking, the problem that stares us in the face is the scarcity of IPv4 addresses. And as these prophets would have it, we will run out of IPv4 addresses, and then we will simply curtail the growth of the internet. No one will be able to get additional addresses, and therefore the internet will remain the size that it is. With humanity growing and people having more and more devices, we need more addresses. So, yes, if it's serious, then we do have a real problem. The truth is, it is serious. Many of the regional internet registries are allocating their last blocks of IPv4 addresses at the moment, and they will run out in the next year or two. Also, there are a couple of other problems associated with IPv4, such as the large routing tables that it requires, that need to be addressed. One of the reasons why we haven't changed sooner is the fact that it is an immense effort to change the IP layer, to change the network layer of the internet. Because in principle, it means the entire infrastructure, all the routers of the internet have to be replaced. And that is costly. That is a massive task. However, the next version of IPv6, has been developed over the past decades, and every piece of new equipment that you buy has it available, it's installed, it's ready to go. And over time, one tends to replace IT equipment anyway. So by now, almost everything on the internet is ready to handle IPv6, and we are in a position where we can really switch over. In fact, many people have already switched over and are using IPv6. So these two protocols, IPv4 and IPv6, are running in parallel, and those who are running IPv6 have access to the huge address space that is offered by IPv6. Many ISPs do not yet provide users with access to IPv6, so many people still have to rely on IPv4. But as I noted, that is definitely a position where we've achieved both the need and the readiness, and we will very soon tend to see more IPv6 than what we see IPv4. One of the questions to ask is, if IPv6 has been ready for a long time, why haven't we switched over some time ago? Well, part of the answer is that the equipment wasn't in place, but part of the answer is also the ways in which we extended the lifetime of IPv4. This extension of the lifetime of IPv4 will be the topic of the next video. In this video, we will look at IPv6. Our focus will be on IPv6 addresses, and we will also say one or two things about the routing in IPv6. We've mentioned the length of an IPv6 address as one of its major benefits. So let's just think about a couple of issues around that length. First thing, it may be useful if you think about an IPv4 address that consists of 32 bits, then there is it more down to some sort of a scale at least. an IP version 6 address will be 4 times as long because it consists of 128 bits. So it will extend for a second 32-bit quantity, a third one, and a fourth one. And I've gone behind my picture there, but you get the feeling that this is an extremely long address. An even better way of getting a feeling for how long it is will be when we write it down, or write an address example down. So let's move on to that. You already know that IP4 addresses consist of 4 bytes, and every byte is written as a number. So in decimal, so 10.2.3.5 is an example of an IP version 4 address. If we were to use the same technique for an IP version 6 address, then that field, as you can see, will consist of 4 times as many words as we started out with, assuming a 32-bit quantity can be called a word. So we will need 4 times as many values to represent an IP version 6 address. That means 4 times 4, 16 decimal numbers. That's just going to be far too long. We need something simpler. The way that they decided to simplify it is to not represent every byte, but to represent every 16 bits. Now, given that this is 4 times as long, you can quickly figure out that you will have 8 such fields. These fields will in the end not be separated by dots like we had in the IP version 4 case, but they will be separated by colons. So let us write down the colons in preparation for writing down an IP version 6 address. We will have 8 fields, therefore we will have 7 colons. So there we have our set of 7 colons to separate 8 possible fields. And now I'm going to write down what an address may look like. This address has no inherent meaning, it's just a random sequence of hexadecimal numbers. We know that every field between colons consists of 16 bits. Therefore, it means we need 4 digits, 4 hexadecimal digits to write them down. So here is our random example. Now, clearly, that is an extremely long address where one may be able to remember an IP4 address. There's no way in which you're going to remember an IP version 6 address like this. More specifically, even if you have to type it from, let's say, some manual into a field on your computer system, you're probably going to make a mistake. And just think about IT support when you were to phone them and they were to read an IP address to you over the phone. It's simply not going to work well. Somewhere you're going to mistype something. So the first option, the first thing that we may do to try and simplify this just a little bit is to ignore the leading zeros. There's no need to write down leading zeros. So we can cancel out that and those 3, we don't need them. We can cancel that one out. We don't need any of those 3. We can cancel those 3 out. And that's it. That was all the leading zeros. And this leads to the following address, which is somewhat simpler, but not really. So there's our address written down, and we've omitted all the leading zeros. You can see that it is a little bit shorter, but yeah, it doesn't really help much. The technique that IP version 6 really uses to try and shorten address is a technique known as zero suppression. So what we've just done, where we cancelled out these leading zeros, that is not zero suppression. What I'm going to do now is zero suppression. So zero suppression is where you have a sequence of fields that are all zeros. And then you say, okay, I'm just going to indicate that I have such a sequence, and therefore I can take them out and put them back when necessary. To make this clear, let's copy down the address up to the sequence of zeros. So there we have the initial part of the address. And now what I'm going to do is I'm going to insert a second colon there. And that second colon, the two colons next to one another, will tell the reader that we've suppressed zeros between these two colons. And we can now copy down the remainder of the address. That is somewhat shorter. I'm still not convinced that it is really easy to read, but it is easier to read or easier to type in than our starting address would have been. So what we have now is something where the recipient, the reader of this address, anyone who looks at it, will see that we've suppressed zeros because there are two subsequent colons there. And they will then take this value, this address, they will stretch it out and insert the zeros again. The logic of this notation is that you will try and assign addresses to computers where there is a possibility that you may have to enter the address manually. Think about an example where you have to enter a default gateway or something like that into some setup, and to assign such a short address with a lot of repeating zeros, even more than what we have in this example if possible. That will enable you to compress your address even more, and that may make it simpler for a user to enter it manually if you are going to enter it manually. However, the assumption here is that you will use a protocol like DHCP that will provide the values and that you won't enter them manually, but at least it gives you some sort of an abbreviated notation for some of the more important machines. Just as an obvious remark, I guess, if you try and use zero suppression more than once, so there is something that purportedly looks like an IPv6 address. We have our values that are in the appropriate range in hexadecimal, and there it seems to be zero suppression, and there it seems to be zero suppression. So in a sense, we have to stretch this out, and we have to insert some zeros into that field, and we have to insert some zeros into that field. But how many? It's unclear, and therefore we cannot use zero suppression more than once. We can only use it for one sequence of zero fields like we've done there. The next aspect to consider with IPv6 is how do you indicate what network you're talking about and what host portion you're talking about. And we will use exactly the same approach that we've used in IPv4. So we will have two fields, and the two fields will consist of our network portion that is now called a routing prefix, and we will have our host portion. Now, given that we are dealing with a 128-bit address, it should be clear that we are using 64 bits for the prefix and 64 bits for the host portion. In this case, they don't even try and make provision for class A, class B, class C, and so on. They've just split it right down the middle. If you think about this, what it means is if you get a routing prefix, if you get a 64-bit quantity, then you should be able to address 2 to the power 64 computers on your local network, because you have 64 bits there available to indicate the address that you are dealing with. Now, just think about this for a moment. We know that the size of the public internet is more or less 2 to the power 32 IPv4 addresses before we start to think about IPv6. So what this means is you can take the size of the public internet that you can represent in IPv4, that's everybody on the internet in essence, and you square that, and that is the number of computers that you can now have on your local network. So the size of the public internet squared on your local network. That is massive. Where do you get a routing prefix? Where do you get those 64 bits? The answer is again the same as it was for IPv4. You will get it from your ISP, and the ISP may get it from a bigger ISP, and eventually they will get it from the Regional Internet Registry, the RIR, Afrinic in the case of Africa and the Indian Ocean Islands, and all the regional internet registries will ultimately get the address space from IHANA, the subcommittee of ICANN that deals with this. The decision is that these routing prefixes will be allocated in blocks to what are known as local internet registries. So that would be a typical example of an ISP party with whom you deal, and they will then be able to assign a value to you. The decision is that for the smallest local internet registries, they will allocate /32 blocks. What that means in practice is that if you are a small local internet registry, they will provide you with that portion. Those 32 bits will be fixed, and then you as the ISP or as the LIR will be able to put different values into that field to complete your address that you will then hand out as a prefix to a user. Again, what that means is, and I keep on repeating this, that we are talking about a small LIR. The small LIR will have the possibility to insert 2 to the power 32 values into that field to complete the routing prefix. 2 to the power 32 is again the size of the public IPv4 internet. So every ISP will be able to assign as many addresses as are available on the public IPv4 internet at the moment. I should perhaps rephrase that and say at least assign that many, because the moment that you begin to talk about a bigger internet registry, then they will start shifting that dividing line that we have there to the left. So instead of a 232, you may have an LIR that gets a 230, which means the first 30 bits are fixed, and this slightly bigger LIR has the remainder of that 64-bit field, in other words, 34 bits that they can use to create routing prefixes for their customers. So as we move to bigger and bigger ISPs, we just move that to the left, and we can assign them shorter prefixes, and they are then able to add more bits to complete longer prefixes. All in all, the prefix will still be 64 bits long, but this is what will then be handed to a customer who needs addresses. Thinking about the smallest of these LIRs, given that they will get a /32-bit field, means that we will be assigning or prescribing 32 bits for them. And with 32 bits available, it means we can have as many LIRs, small ones, that exist as we have hosts on the public internet at the moment. Because yet again, we have 32 bits, so 2 to the power 32 possible LIRs for every machine that is on the internet that has a public IP address at the moment. We can create an LIR. Obviously, as we make some of them bigger, we reduce the number, but it is still an amazing number to think about. So there, in principle, we have the size of the public internet. There we have the size of the public internet. And then for every network operator, whether you're an individual, a small company, or a large company, you have the possibility to have the number of hosts that are on the internet squared at the moment and use that to address your local machines. So clearly we are talking about massive increases here in what can be done. As we noted, your one option is to obtain an IP address, or more specifically a routing prefix, from a local internet registry, from an ISP. And once you've obtained that prefix, you can use it and you can combine it with host addresses or host portions, host suffixes, and they will form your addresses that you can use on your internet, and they're all fully routable through the public internet. There's no problem getting them from one machine to another machine anywhere on the internet. However, we may also want to think about the possibility of using private internet addresses. Remember that in the case of IPv4, we had the possibility of using addresses, A addresses in the 10 range. We had some examples from B, and from C we had all 256 addresses in that address space that we could use for private use. So you could just assign them and use them. They were not routable, but at the very least, you could assign them and use them without asking anyone's permission. Question is, do we have something similar in IPv6? And the answer is yes. In IPv6, all private addresses start with a bit pattern 1111. Going to leave a little space there so that we can easily read the nibbles a little bit later. But this pattern then continues with another 1, and a 0. So 7 bits in total. And whenever you see those 7 bits at the start of an address, then you know that it is a private address. Typically, we do not express these addresses using binary. Typically, we express them using hexadecimal. And what you should recall is that we will represent the first 16 bits in any given field. The first 16 bits in the first field and the second 16 bits in the second field, and so on. So since we are talking about the first field here, we somehow need to pad it out until we get to 16 bits. And the way in which we pad it out would be by zeros, so we'll have to pad it out by 0 there. Next nibble will also be zeros, and the final nibble of that 16-bit field will also be zeros. So this would obviously translate to F, that would translate to C, that would translate to 0, that would translate to 0. But we should keep in mind here that only for the first 7 bits up to that point were the bits that indicated that this was a private address. Hence, formally, a private address is characterized by the fact that it starts with FC00, and then we can use our colon to indicate zero suppressed zeros right until the end, and we would say that /7, in other words, we are using the prefix, the first 7 bits here as our indicator. Let's now turn our attention to a rather special type of private address. Being private, it will start with 1111, 110, just like any other private address would, but then it, in the first field that seems to be under user control actually, it will have a 1 to indicate that it is this particular type of private address. So same thing, to represent it before we talk about what it does and how it works, we need to pad it out. So here in the first 16-bit field, we've already used 8 bits. So to pad it to a 16-bit quantity, we'll have to add more zeros. There is our first field in that address. This is still an F like it used to be. This is a D, that is a 0. And that is a 0, and it's the first 8 bits that are imported. So this category of addresses are characterized by the fact that they start with an FD00, and then we use colon, so suppressed zeros, and the prefix that is important is 8 bits long. Before we even proceed to what this category of addresses is used for, let's just point out that this is indeed a private address because it starts with the same bit pattern. Its initial 7 bits are identical to what we had in the general case. So in the special case, we are dealing with a private address. First 7 bits are identical. However, it does not translate to FC. It translates to FD. So there's a general message when we begin to look at the length of prefixes that are not necessarily on nibble borders. Then we may end up with values that look rather different, but in terms of the significant bits, they are the same. Let us talk about this category of addresses, this second or special category of private addresses that we've mentioned. The fact that we already know about them is that they are characterized by the fact that the first 8 bits are marked by putting those 8 bits into it. So we can recognize this special address by the presence of those 2 nibbles or that specific bit pattern. The next thing that this private address does is it allocates 40 bits to be random. In other words, if you want to create one of these addresses, you will just think of any 40-bit random number. Depending on how you define a million and a billion and so on, that would be 10 to the power 12. So a million, which in some cases, places in the world will be a billion, and other places in the world will be a trillion. But you have a 1 in a trillion possibility then of picking a specific random number there. And again, we will explain the significance of that in a moment. The next 16 bits are used to indicate a subnet. So you can talk about this general address that you've created, and then you will also be able to create subnets within that. Now, if you add up these bits that we've used, the fields that we've used, then you will see that up to this stage we've used 64 bits. So this is a nice routing prefix already. And in particular, what you can, for example, do with the subnets is if you have different branches and they may even be on different continents, you can in principle route to them using these subnets, or distinguish between them using these subnets while you're using the same prefix. Do, however, keep in mind, while I've said this, that we are talking about private addresses, and private addresses are by definition not routable like public addresses. So we are talking about routing within your infrastructure, not in a general infrastructure. Now, once you've come up with an address like this, it means you have 64 bits that remain for the host portion, and you can just simply go ahead and number the machines that you are using 2 to the power 64 possible addresses for hosts in each of your 2 to the power 16 subnets that you may create. So this is the mechanism how this works. Why on earth would you want to create an address like this? And the logic is the following. Suppose you have an organization and you want to use private addresses inside this organization. Suppose there is another organization, and let's use the one case where we can immediately see the benefits of it, and that organization doesn't want to assign public addresses to its customers. It rather wants to interface to their customers using private addresses. If you look at the IP address on your cell phone right now, which is probably an IPv4 address, chances are that you will see that the ISP is working on a private address, not a public address. So your ISP, your network provider on your cellular phone, has a public address that goes out to the world, but inside the ISP, it is using a private address. One particular example in the IP4 world is where the ISP, for example, assigns addresses in the range of 10.0.0.0, and where the problem comes in, if on your own network, because your network is also a private address network, and if you were using IPv4, then you could have been using the same range, and then you would have a router that connects those two instances together, and this router is totally confused by the fact that it has to route from 10 to 10. So the problem that we are facing here is that while anyone is allowed to use a private address, in this example, the ISP and your organization are both using the same private address, and therefore, even in this case where private routing does occur, it doesn't work. Now, just imagine if you could put a 40-bit random number in there, and the ISP would put a 40-bit random number in there. Then the odds are extremely small, 1 in a trillion, that you would pick the same random number, and hence you will have different addresses. So that's where this category of addresses fit in. If you create your own private addresses in this range, using this mechanism, and some organization to whom you want to connect that also uses private addresses, they put in a 40-bit random number in their choice, then the odds are that you will have an address here that is not the same as the organization you are connecting to, and therefore you are able to route these private addresses between the two of you. In general, it remains true that private addresses will not be routed across the internet. You can begin to think what the odds are if you are picking a 40-bit random number, that you will pick a number that is the same as anyone else on the internet that uses this mechanism. Before you start to think too much about that, just look at the birthday problem again. where the question is, what are the odds that two people in a fairly small group of people will celebrate their birthday on the same date? And the odds are shockingly high for even small groups. So don't assume that because this is a 1 in trillion, using that notion of a trillion, 1 in trillion chance of picking a specific random number, the odds that two organizations on the internet will pick the same address are significantly higher. So you cannot rely on this mechanism to give you a unique address. In any case, this address, which basically has a random routing prefix now, becomes very hard to route to because you don't know where in the world it is, and hence the routing tables will not know about it, and it's not globally routable. But routable in a local context between a small number of organizations that decide to interconnect, this is a perfect strategy. IPv6 also makes provision for auto-configured addresses. So these are not addresses that are assigned in the sense that you would assign private or public addresses. They are just calculated for any interface. So one of the things that one should clearly distinguish between, in general, we tend to talk about the address of a computer, but it's really the address of the interface. And there is the loopback interface, which provides you with connectivity to your own machine. And then there are typically Ethernet cards and other wireless interfaces and so on. And they all can have addresses, and those addresses are different. So what we're talking about here is an address that is auto-configured, not for the computer, but for the specific interface, just as typical addresses would also be assigned to an interface rather than a computer. Just as a reminder, we spoke about the addresses that have the pattern 1111110 as the category, or the addresses that are private. And then we also spoke about those that start with the pattern 11 and so on, and eventually 1101. So those translated to FC00 slash colon slash 7 and FD 00 colon slash 8. And those, as we said, were private addresses. The auto-configured addresses start with a pattern 11111110. So they are clearly not private addresses. This is a different category of addresses. So we have public, private, and then auto-configured. These addresses go a little bit further in the sense that they also include another bit or two, in particular 10 at the end. And in general, they will be FE80 colon, so 0 suppressed and 10 bits long. The principle behind these auto-configured addresses is as follows. We are using this 10-bit pattern to indicate that we are dealing with one of those addresses. So that pattern goes into the first 10 bits, and then you need something on that interface that is unique. Now that something that is unique is the MAC address. MAC addresses, media access control addresses, is something that we will only consider once we get to layer 2, because access to the medium is a layer 2 function. But that address, that MAC address, is available to layer 3 to extract if it wants to. The MAC addresses are globally unique, and they are 48 bits in length. So globally unique, when you buy a network interface card, or when you buy a cell phone with Wi-Fi and perhaps Bluetooth and so on, they may have, on all those interfaces, they will have different MAC addresses. There are some extraordinary cases where one can assign a MAC address. But in general, you can't assign a MAC address. It's burnt into the electronics when that chip is manufactured, and therefore they will be unique. And we can put that 48-bit field after some processing to transform it into a slightly different form, because we don't necessarily want to put the MAC address in there. We will end up with a value that is unique. In fact, we will look at an example of this a little bit later. These addresses are indeed globally unique because they make use of this 48-bit field that is globally unique. But clearly, it's going to be hard to route to them in general, because when you buy a piece of network equipment, that MAC address says nothing about where you are. So to get the message to you, wherever you may be, is more or less impossible. But if you are, for example, talking about computers that are sitting on the same network cable, then it's very easy to say, I've got someone's address here, and I'm going to send it out, almost broadcast it. We'll have something to say about that in a moment or two. But then we are able to talk amongst computers on the same local area network, on the same piece of cable, or in the same Wi-Fi area, without needing any special address. So this address is local, although it is globally unique. In general, these provide you with your easiest option if you just want to begin to play with IPv6 addresses, because they are most probably already assigned to your network interface cards. It is time to say a couple of things about routing. In IPv6, we will be routing in essentially a similar way to what we used in IPv4. So you will have your routing tables. The routing tables will contain a network prefix, a network address, as we've seen in IPv4, and they will contain a next hop and a packet that arrives at a certain node. The address of that network, or the destination address of that packet, will simply be looked up in the routing table, and then it will be forwarded to the next hop. So nothing really interesting there, with perhaps one exception that we need to take note of, where if you are routing to two networks in IPv4, you will have two table entries for those two networks. But if you can somehow in IPv6 determine that a part of the path that adjacent network addresses should follow, in other words, if a message is sent to an address A or an address B, and for a part of their path they have to traverse the same network, you can aggregate those addresses. In other words, you can say, I'm going to, in a sense, almost supernet it, and then route to the point where the paths have to be different. And that enables you to have smaller routing tables, and obviously will typically again involve a regional internet registry, because you will need something, for example, to say that these addresses are in South Africa, therefore you're going to route them to South Africa as if they were one big block, and then once they get to South Africa, then you start looking at them in finer detail, and you use less aggregation, and you may eventually use the specific prefix to deliver it to its destination. When we talk about routing in IPv6, we also have to introduce some terminology that is not entirely new, but that is commonly used in IPv6. The terminology that we are introducing are all based on the notion of broadcasting, but IPv6 doesn't make provision for broadcasting. So it's this casting suffix that we will be using. And the first of these is unicasting. Unicasting is when you are sending something to a single machine, to a single interface, and there is no notion even of broadcasting it, but for whatever reason they decided to use the term unicasting for that. The second term that we have to introduce is also not new. Multicasting is, as we've seen in IPv4, when you are sending a message to members of a certain group. For example, if you are sending a message to all routers, then you are multicasting it to all the routers, to everybody in the router group. Multicasting in IPv6 is improved. It can do a couple of things that you can't do in IPv4, but we do not have time at this stage to go into the details. And then the final casting that is added by IPv6 is Anycasting. Anycasting happens where you have a couple of servers that are able to process a message. Let's use a web server as an example, and a company that has an extremely busy web interface may, for example, have multiple web servers that are all serving exactly the same content. And what Anycasting says is this should be delivered to any one of those servers in that pool. So whichever server gets it, it will be one machine, one server that gets the message, and it will process it and respond to it. But rather than doing some sort of manual load balancing where you are sending your messages to different services, you simply use the Anycast mechanism that is provided in IPv6, and it will then be delivered to any one of the servers in the pool, effectively providing you with redundancy and load balancing. As you recall, localhost in IPv4 is that rather special address, class A address, what a waste. But anyway, in IPv6, the localhost is simply all zeros followed by a 1. So again, we will use that in an example in a moment or two. A possible question is the following. If you already have an IPv4 address, can't you use it to generate an IPv6 address? IPv4 addresses are only 32 bits in length, so they will fit easily into an IPv6 address space consisting of 128 bits. And the answer is sort of yes and no. So let's look at the yes part and then we look at the no part. The recipe to create an IPv6 address from an IPv4 address is a rather simple recipe. Say that that is your IPv4 address and you want to represent that as an IPv6 address. Is that a way of obtaining an IPv6 address? The logic of this is if you already have an IPv4 address, that's only 32 bits in length. In IPv6, you have 128 bits available, so it should be pretty easy to fit it in, at the very least. However, what becomes the prefix and so on is where the devil comes into the details. So the notation change, or the mechanism that's used to represent this as an IPv6 address, is that you simply add 16 ones in front of that. Now here I'm going to write this in hexadecimal, and then you've used your 32 bits there, you've used 16 bits there, and in everything that precedes that you just put zeros. So to write down this address as an IPv6 address, you will say colon, because you're suppressing all the zeros initially, and then F, and then colon again. And now, in principle, you should translate this lower part. You should translate that to hexadecimal, but IPv6 provide a convenient alternative, because once it sees this FFFF, it knows that you're now providing an IPv4 address, and you can provide that using dotted decimal notation. So there is your address converted to IPv6. Now, if you really feel strongly about it, then you can go and think about the hexadecimal representation of those bytes. So as a byte, 10 will be 00001010, and that will just be 000 and eventually a 1, and the same 0 and eventually a 1 and 0 and eventually a 1. Now combining these 2 bytes and those 2 bytes will give you a 0A01, and that will simply give you a 0101. So writing this as 16-bit fields, I can say prefix is all zeros. The FF is already in hexadecimal, so I now simply have to write down the remainder, which happens to be A01, and that happens to be 101, and I have an IPv6 address that is specified in all hexadecimal pure IPv6 notation. So that, as I said, is the good news part. Let's now talk about the bad news part. If you look at the layers with which we are working at the moment, then your stack will, on layer 4, which is somewhat above where we are right now, probably have TCP, and it will have UDP, and on our modern systems it will have QUIC. So that's layer 4. On layer 3, you will probably have a dual stack, in the sense that you will have IPv4 and you will have IPv6. And then you will have your specific network interfaces that begin. So you may have Ethernet running on some of them, and some other layer 2 protocols that we will talk about later running there. Now, what will happen with this particular IP address is, as it traverses down the protocol stack, it will realize that when it arrives on layer 3, that this is an IPv4 address, and it will send it through the IPv4 version of the protocol. So there's no way that you can send this to another machine where your peer node on layer 2 happens to be an IPv6. You can only send it to something where your peer layer is IPv4. So this mechanism is purely a syntactical convenience for you to represent an IPv4 address in IPv6 notation, but you are still using the IP4 version of the network. You are not using IPv6 of the network, and hence this will not enable you to talk to other hosts that have IPv6 software on it. You cannot convert your IPv4 address to an IPv6 address and use it to communicate to the outside world. To a large extent, it makes sense because routing happens on the prefix part. So you're on the left-hand side, far to the left, in fact, whereas here your network part, your old network prefix that we spoke about in IPv4 is low down in the host part. So it sort of makes sense that it can't root on something that occurs that low in the address space. But again, we will demonstrate that in a practical example in a moment or two. Whereas IPv4 headers may differ in size because they contain option fields that are not of a fixed size, IPv6 headers have a constant size. And then if they use options, they use what is known as optional extension headers. This fixed structure of a header makes it simpler and more efficient to route. Let us now use a couple of superficial examples just to illustrate some of the issues that we've encountered. I have two computers in front of me. The one is a Linux machine, the other one is a Windows machine. Obviously, we are looking at the Linux machine at the moment. So if I want to see the interface configuration on that, the command is ifconfig. And what you will see immediately from the response here is that on the loopback interface, we are getting an IPv6 address as we would have expected, ::1. And then on the Ethernet 0 interface, we are also getting an IP6 address. And what makes it interesting here is we can see that that is an auto-configured address. We can also see the 0 suppression there and the prefix length, which happens to be 64, which is more or less what we expected. I'm just going to copy that, and then I'm going to go to the Windows computer and I'm going to ping that address that we've just seen on the Linux computer. And there you can see that we are getting the response back, typical Windows behavior. So we are getting 4 responses. And in the opposite direction, if I do an IP config here, I will get the IP address of the Linux, of the Windows machine, but not only the IP address, I will also get the various interfaces that are available. So there is the interface that we are looking at. I'm just going to scroll it a bit lower. So the interface address that we are using, or the IP address on that interface, which is the Ethernet adapter, happens to be that. You will see in some cases that there is a percentage sign after it, and then the interface number or the interface name will follow that. We will see that in 1 or 2 examples where it will become more obvious. So let's copy this address. So I've copied the Ethernet address on the Windows machine. I am now going back to my Linux machine, and I'm going to ask it to ping the Windows machine, and we are getting the responses back as we would expect. One of the things that I promised to point out is here we're getting the responses back, and we are getting it back via the Ethernet 0 interface. Now, why this is important here is because these interface addresses have been generated for specific interfaces. Now, this is the interface on which it encounters that. Obviously, it is an address that's been generated on the Windows machine and on a very different interface, but this is the interface through which we get it. And sometimes when we use these auto-configured addresses, it is important to specify the interface through which we want to access it. On this Windows computer, let's say that I now want to ping the computer that we spoke about during an earlier part of the video, pinging it with IP version 4, and clearly that is doing what I would expect it to do. However, we can also ping it using IP version 6, so that, if you recall, would be FF, so 0 suppressed zeros, and then FFFF. And after that, I can change my notation to the IP version 4 notation, and you can see that I am getting my responses back as I would expect. We also calculated a different representation there, which, if necessary, you'll have to go back to the video and look at that, and you will then see that it was FFFF, and in hexadecimal it was A01101, and what you can see is that this is indeed working. But one of the interesting things is that the return addresses are IP version 4 addresses. So here, where I am pinging it using an IP version 6 notation, I am really pinging it on IP version 4. I am using the IP version 4 stack. Where we can begin to break things is if I were to say ping an address and I specify that it should use IP version 4. Just to show you that this does work, if I use IP version 4, then I do get a response back from that particular machine. However, if I say that it should use IP version 4, and then I specify colon, and then FFFF, and then 10.1.1.1, in other words, the IP6 notation of that address, then it doesn't understand the IP version 6 notation. On the other hand, if I go back and say, okay, let's use IP version 6 for that address, then it can't send that via IP version 6. It fails. In a sense, I need something of both. I need the IP version 6 to interpret that address, and then I need the IP version 4 protocol stack to transport that for me to the other machine. Let us also just quickly ping the localhost, which, as you know by now, is ::1, and I am getting back my responses as one would expect. This has been a rather superficial introduction to IP version 6. We mostly looked at addresses and a little bit at routing, but IP version 6 offers many more benefits. As one example, IP version 6 is more capable of dealing with users who are moving from one point in the network to another point. IP version 6 also makes provision for a number of additional facilities with its various extension headers that we just mentioned but didn't discuss. IPv6 also introduced IPsec, the security standard to be used on IP. However, that was backported and also applied to IPv4. So that is already available in IPv4, but it still is an accomplishment of IPv6. And this list goes on. And yes, we simply can't cover all of it in a module such as this. In our next video, we will ask the question, why was IPv4 able to survive for such a long time, even though we should have run out of IPv4 addresses, even though IP4 routing tables should have grown too big long ago? All of that in the next video.